So, okay, let's move to the next speaker, which is Mercedes Gimeno-Segovia. You can share your screen whenever you're ready. She's the Senior Director of Quantum Architecture at PsiQuantum, and she received her PhD from Imperial College of London for her work on linear optical quantum computing architectures. He did her postdocs in Bristol and Calgary, and joined PsiQuantum in 2017. And where she leads the team working on design and developing architectures for universal fault-tolerant quantum computation with silicon photonics. So, and I believe that that's precisely what she will present today. So welcome, Mercedes. Thank you for joining us, and whenever you're ready.
Yeah, thank you. It's really a pleasure to be here. And I share Sophia's feeling that it's great to have be here among like estimated colleagues, and I look forward to the discussions afterwards. Okay, so today I want to talk about fault-tolerant quantum computing with photonics, which is the approach to quantum computing that we're pursuing at PsiQuantum. And in particular, I want to discuss these architectures in the newly introduced fusion-based quantum computing paradigm, which is the computational paradigm that we use at PsiQuantum. This is a new framework that is focused on the efficient integration of quantum error correction and physical level hardware operations, which is applicable to many platforms for quantum computing, but it's particularly applicable to linear optics. So first, I wanna get started on why we use photons. So photons have a number of very good advantages, and here I'm only mentioning a few. Particularly is the fact that we can have fast measurement and clock speed, and this fast measurement really allows us to remove noise from the system early, which means that we can unburden our error correction code to be able to cope with higher errors in our hardware. Photons do not interact, in particular when we are in the single photon level with linear optical operations, and that means that we lead to having no quantum crosstalk. And finally, geometrically, photons are not constrained to being in a particular place in space, and actually this allows to use this physical scheme to explore higher dimensional error correcting codes and systems that really open up new doors for error correction. But not only do we use photons, but we also use a particular encoding in photons, which is dual rail. So dual rail is particularly useful because as opposed to single rail, loss is heralded. We detect when it happens, and protecting against heralded errors is much easier than against unheralded errors, and we can achieve higher thresholds. And we can achieve very clean linear optical operations, as well as have a relaxed phase stability requirements. Not only do we pursue dual rail photonics, but we also pursue it in a physical platform, which is silicon photonics. It has a number of advantages. For example, we can achieve very low noise thanks to the really good design and tools that are available to do that. It's an inherently scalable platform because we do not need to have millikelvin temperatures. Our photons can connect directly from a silicon photonics chip onto a fiber, an optical fiber, the ones that are the same that are developed for optical communication without the need of transducers. And really we do not need any atomic scale fabrication. So all of this really convinces us that this is a platform that can scale to a full fault-tolerant quantum computer, because the step change from having a few qubits to having hundreds of logical qubits, really several orders of magnitude, which are needed to implement error correcting code. Okay, so I want to talk a little bit about how do we encode our qubits, what are the operations, before I move on to the architecture itself. So we use dual rail photonic qubits, where we are encoding information in the path degree of freedom. So for every qubit, we have two waveguides, and if we have like the presence of a photon in the top waveguide corresponds to a logical 0. The presence of a photon in the And the second waveguide corresponds to a logical one. Now you can see now what I meant about loss being heralded, because we are always in the subspace where we have a single photon between two waveguides. So if at any point we detect either more than one photon or less than one photon, then we know that some error has occurred. In particular with loss, which is our the main source of error for a photonic system, it's heralded in this way. Single qubit gates are implemented by doing Mach-Zehnder interferometers, or a generalized version of them. So here we have these directional couplers, these 50-50 couplers, which are acting as 50-50 beam splitters. And how they're very simple in the sense that all you're doing is bringing those waveguides that are doing your that are encoding your qubits. You're bringing them close together for long enough, such as the field from one of them can evanescently couple to the other one, implementing your beam splitter. Phase shifters can be implemented by a number of different methods. They can be thermo-optical, electro-optical phase shifters, and really the implementation depends on the platform and the specification and requirements that you have for that operation. So single qubit gates can be implemented very easily, and in fact there's a huge volume of literature in silicon photonics implementing and showing how many of these operations can be done. And in fact, at the example that Sophia gave on like the first paper on VQE implemented as an experiment was done in a platform of silicon photonics. 2-qubit gates are slightly different. So CNOT gates can be implemented in linear optics. And in fact, it was Jeremy O'Brien's group as well, I believe, that showed the first CNOT gate with silicon photonics. However, they're not the most natural 2-qubit gate for photons. And in fact, those gates, the more natural gates, are what we call fusions. They're more natural because they basically consist on some passive interferometer, and the simplest one of them, type 1 fusion, is literally just one beam splitter and 2 detectors. And when we do that, we can use these operations to do a probabilistic operation on our states. So in this case, for example, we have that we have two states, and we are putting 2 of those photons through the gate. Now you will notice that I said qubits have 2 modes. So here what I'm doing is I'm taking one mode out of each qubit and mixing it here in the interferometer I'm measuring. And a particular detection pattern will herald success, in which case I will have generated a larger entangled state. And in some cases, when it failed, when the detection pattern tells me that it's failed, I get a different state. Now, what is important to note here is that even though my operation may have succeeded or failed, I am still recovering stabilizer operators that describe my state. So all of the outcomes of these fusion gates, they correspond to stabilizer measurements. And the crucial thing is that these stabilizer measurements, they can be used as check operators in a quantum error correcting scheme. And the other thing is that really, I'm putting here an example, but there's a flexibility on how you choose your passive operations to determine exactly what stabilizer operation you're doing on your state. And really, you can start interpreting failure of your gate. For example, in the case of a type 2 gate, you can interpret the failure of your gate as the erasure of some stabilizer information. And really, erasing stabilizer information is something that error correcting codes are really well prepared to deal with. And then one final note is that you see here the simplest entangling gate, which is a passive interferometer followed by some measurement. And this is really the genus of all of the entangling operations that we do in linear optics. They are probabilistic because we are in the dual rail space. And really we can use this same principle applies to many other situations that I'll show you in a second, so that you can build entangled states. So for example, we can, like the same principle applies of, we create, we apply a particular interferometer, a passive interferometer, and we do measurement of a subset of the modes. We can use this principle to generate entangled states, so 3-gate set states, from single photons. The same principle can be used to get from these 3-gate set states, combine them in some particular way, and generate a larger, more complicated entangled state. So you can start building what we call resource states, which are small states of constant size, be a sequence of fusions that you apply to their qubits. Now, it's worth noting that each of these steps is probabilistic. However, it's not only probabilistic, but it's heralded. So you know not only when it has succeeded or failed, but you also can detect errors early, because if, for example, imagine that one of the photons here in the left had been lost, I have a certain high chance of detecting that I have a different number of photons that I was expecting here. Maybe I don't catch it here. Maybe I catch it at the next step where I'm expecting a photon and I don't get it. But this sequence of heralded operations really give us information about the errors. And what we can do is, whenever the operation fails or we detect an error, we can switch out the states, or we can do multiplexing, which basically means we repeat an operation several times and we select the one that has succeeded. The other important point is that this leads to only constant overhead, which means that to generate a particular resource state, we only need to we will need to generate a constant number of extra photons and have extra resources. And this probabilistic nature of the operations, because we are using multiplexing, does not lead to any exponential scaling. And this is a question that comes out often, and actually this is the basis of the original KLM architecture that was proposed in 2001, showing that linear optical quantum computing was indeed feasible. But now we need to go from feasible to something that is practical. So we have been, at PsyQuantum, we have been working on fault-tolerant architectures that are motivated by photonics. And really the goal for us is to achieve fault tolerance using natively photonic operations. And there are different aspects that we have been focusing on. First is reduced classical processing. So previous architectures for linear optical quantum computer require a lot of steps of quite complex classical processing, particularly those architectures that use percolation. And that meant that while that computation was occurring, our photons were stored in fiber and they were waiting and they were subjected to loss. So that's something that we wanted to remove. We also wanted to have photons that have a very short word line. That means that the number of components since the moment that photon is born in a source until the moment that is absorbed at a detector, we want that to be the minimal possible, so that there's a very small amount of errors that are accumulated through the life of the photon. Most importantly, we want that word line does not depend on the algorithm that we are implementing or the error correcting code itself, so that as we scale the computer, as we run different algorithms, that photonic word line remains constant. And finally, modularity is key in order to build large systems. We can build maybe one bespoke large system, but really when we are going into something where we want to be able to expand to like increase the size or increase the capabilities, modularity is really key. So that's one of the things that we are focusing as well. So with all that, we have been working on this new fault-tolerant framework for quantum computing for a while, and we published a paper recently in January on the archive on this topic. So if you're interested, a lot more detail than what I'm going to talk about are going to be in that paper. And the interesting thing about this framework is that even though it was inspired by photonics, because that was the particular platform we were working in, it's really generally applicable. So the this framework has some primitives. So one of the first primitive is a resource state, which are small entangled states of a few qubits. And these resource states, they have a constant, so for one particular architecture, they will have constant size, and they are always, we are focusing on them being stabilized states, mainly because stabilized states are much easier to, not to deal with, but a lot of the error correcting codes that exist and that are well studied are use a stabilizer formalism. The other important thing that I will emphasize a little bit later is that because they're small, the amount of error that can have been accumulated on the generation of that state really is usually low, but most importantly is constrained. And secondly, we have fusion measurements, which are projective entangled measurements that I have shown you already. And usually they give us, because they are projective entangled measurements, they give us a number of bits. So you can think of, they can be multipartite, but the easiest and most useful, more useful schemes have fusion measurements of 2 qubits, so equivalent to L measurements, and they give 2 measurement bits, which are the stabilizers XX and ZZ, for example, if those have been chosen to be like that. And the measurements now can be erased, so we may lack that information, or they may be flipped because they have we may have a Pauli error, and those measurements are then, the outcome of those measurements are treated as part of our error correcting code. So once we take that, so we have resource states and fusion measurements, and then we have a fusion network, which basically describes a particular structure in which resource states are fused together according to certain rules. And now this does not necessarily mean that this is spatially or temporally, this is more abstract, but then it's easier to translate into kind of a space-time paradigm. Now, the structure of this fusion network is really designed such that the outcomes that of those projective entangled measurements are, so we are doing the entangling measurements which create this long-range entanglement across this lattice, but at the same time they're providing the outcomes that we need in order to compute the check operators of the error correcting code that is implemented. And now you can see here why it's really interesting that we have very small constant size resource states, because we have small constant size resource states, which means that any errors that have been, any correlated errors across any of those resources that have been generated are really constrained to one part of the lattice, and they do not expand across entire blocks, which might become logical qubits. So, we call it FBQC, fusion-based quantum computing. It's very reminiscent of MBQC, so I want to quickly make a disambiguation to clarify. So there's 3 main differences between MBQC and FBQC. First is that in measurement-based quantum computing, the resource state that is prepared, it has a size that is dependent on the algorithm. You want to run a longer algorithm, you need a bigger state. You want to add more qubits, you need a bigger state. Whereas for fusion-based quantum computing, the size of my resource state remains the same. If I want to run a longer algorithm, or if I want to have more qubits, I need to add more states, not bigger states. And that really makes a difference in terms of the correlation of errors and the resources that you require. Secondly, is that in measurement-based quantum computing, the measurements are single qubits, whereas for fusion-based are 2 qubits. And the third one is that fault tolerance in MBQC is kind of an add-on that you add on top of your cluster state generation. There are 2 independent processes, whereas in fusion-based really is that your error correcting code is its structure is encoded in the structure of the fusion network, so you use it to build it. Okay, so I'm gonna show you one example of an FBQC scheme. This is what appears in, is one of the examples that we give in the paper. So for example, and this is the best performing one out of the ones that we show. So you can have a resource state, which in this case is a ring of 6 qubits. So this is the graph state representation, but you have, those are the stabilizers that describe it. And the fusions is gonna be very simple. It's just a Bell measurement. So then the network is you describe it as a in unit cell. So each unit cell is going to have two, so the ones that are highlighted in purple, two of these resource states, and then we're going to be doing fusions with the neighboring cells according to this rule. So you can imagine that really your full computation happens by like the tiling of many of these blocks. And finally, you have a decoding scheme which is related to your network. So the decoding scheme is described here as a syndrome graph, which is then what is decoded by minimum weight perfect matching, union finder, whichever decoder that you want to use. Where now you have that the vertices represent the parity checks of your code, and they have incident many edges, and then the edges of the graph represent the single fusion measurement outcomes. So by this basically tells you what is the data structure that you need to process in order to tell if there has been an error in your qubit or not. Now, so far I have been telling you a lot of the microscopics about how do we correct errors at the physical level, but really, what we want to know is in order to do quantum computation, we want to do some logic. So logic really requires us to look at the macroscopic features, the topological features of the graph that we are building. And for example, here I have a very simple example whereby creating some specific graph and smooth boundaries, we can create an identity gate. Now, I don't have time to go into the details of this, but there's a paper coming out from our group which describes this in a lot more detail. Okay, so far I've been telling you about the photonic architecture for FBQC, and this has so far become kind of very abstract. So in order to help to visualize it a little bit, I want to show you some kind of the like how it might look like in terms of the physical architecture. So you can imagine, in time, you can imagine that each of these resource states, like you're generating layers of them, and then you're entangling them with their neighbors, and some of them you're keeping them alive to the next round. So something like this, right? Like, so you're generating these resource states, and then they're generated, they're immediately measured, and that's it, right? So in a sense, you can see that really we have achieved this goal of having a very short time line for our photons. So you have like these states being generated, they're being fused with their neighbors. Some of them are remaining alive. Some of the qubits are remaining alive long enough to measure with the neighbor that comes at a time step one after, so that we can create really entanglement across a space and time. So we're using time as a third dimension of our code. So in terms of what that means for an architecture, it means that we have some resource state generators, which are on a clock, generating states. Then they go into a network that basically takes the right states to the right fusion network, the right neighbors to be fused to, and some of them have delays so that we can fuse with the previous time step. We have a number of fusions, and then those fusions they can perform reconfigurable measurements in order to be able to implement logic. And then finally, the output of those measurements go to a classical processor. Basically, this classical processor is in charge of both receiving the information, processing it, decoding it, as well as sending the fusion device setting so that we can implement some algorithm. Now, I think something interesting here is that you can see that it's completely decoupled. The time scale on that my resource state generators are producing resource states is completely decoupled from this top classical processor, because it doesn't need to be sending a lot of information, and that's really helpful once you start thinking about the classical processing architecture. Now, so far, I have been telling you a little bit about the physical architecture, but I have not covered at all anything about error analysis, methodology, etc. So in the paper, we covered this, and there's a number of graphs and a particular toy example, with a toy error model where we do the full calculation. But really, this, we're working towards building one such device, and in order to do that, toy models are not enough. So what we have been developing is a multi-scale numerical model that allows us to capture over 25 sources of errors in components and trace their impact all the way through logical gates. So the way we do it is that we start with some FDTD simulation, verified models of our individual hardware devices, such as the directional coupler that I told you about. These models feed into second quantized simulation of specific circuits, for example, Bell state generation or fusion, which then in turn, these feed into tensor network simulations of large layouts of resource state generation, for example, which then progress into capturing entire fusion networks. And finally, we go all the way up to decoding entire logical gates that are built from these fusion networks. Now, this has been the work of the entire architecture team. It's been like over 2 years of work, but really it allows us to calculate the impact that, you know, the change in the line edge roughness of our directional coupler or the change in efficiency of like one source or one detector has at the level of the logical performance of our computer. So with that, I'm finishing up. I just want to like remind you of the key concepts that we covered, which were we talked about the implementation of the linear optical quantum computing primitives with silicon photonics, in particular these fusion gates, which are the more natural entangling gates for photonics. I told you about this new framework for of fusion-based quantum computing that is in that paper that I'm referencing here at the bottom of the slide. And finally, we talked a little bit as well about the physical architecture, like how does it look like once you take this abstract concept and this abstract framework and try to turn it into an actual device. And with that, thank you very much, and let me know if there are any questions.
Thank you very much, Mercedes. Very interesting. Okay, I can see already many hands raised. So let me check. Please, Alireza, go ahead.
Yeah, I have a question. You may mention the answer, but I anyway want to ask again. I was thinking about, for example, a chemistry problem. Of course, when we have a more complicated ansatz, we need a deeper circuit. So the probability of success reduced. But later you said that in FBQC, we have a size independent. I mean, the circuits should be size independent. We have a fixed size, but we have to introduce more state. I was wondering if having more states reintroduce the problem we have for the success probability, because for each state we have this probability to get a success.
No, and in fact, whenever we are doing simulations of this, so like, you know, this kind of full stack of simulation that I showed here, really we are taking in like multiple resource states with the probabilities that each of them are generated, and simulate entire fusion networks and their performance. So this problem is it's not reintroduced. I think let me just mention, like, kind of related to your question, which is here, like all that I have been talking about is fault-tolerant quantum computing, which means that I am building entire logical gates. So if I want to run a particular chemistry algorithm, what I would do is take that algorithm, I would compile it, right? So I will break it down into into a set of gates that are the ones that we implemented, and then we would implement those gates. So and that's, you know, something that I've not been talking about. We have at PsyQuantum, we have an applications team that actually does, in a sense, the top end of the stack. So here I've stopped at logical gates, but we have a team that is able to go and say, take a quantum chemistry algorithm, for example, and then break it down into primitives, do compilation, you know, and then, like, with, you know, taking into account what are the logical error rates that we want to be achieving, we can trace that all the way down and tell exactly how good my resource states need to be, and like we can estimate from that what would be the size of the machine that we need to be running, for how long would it be running. For example, time is something that I have not spoken about, which is, you know, there's always a trade-off. I can do more things in parallel or more things in sequence, but there's a trade-off with the timing. That's a whole other study that I've not covered.
Mm-hmm. So you don't need to measure for each state separately.
No, so each state separately, it's so in a sense you can imagine that you have multiple resource state generators that are each of them doing independent thing at the same time. You can also imagine generating that network by having the same resource state generator generate multiple copies of the resource state. And actually that is an idea that we explore much further in another paper that came out last month, which is, I think it's called Interleaving Modular Architectures for Fault-tolerant Quantum Computing, that you can take a look at. Maybe that would be useful.
Okay, thank you. Unfortunately, we are running out of time, but please stay connected because we will continue the discussions, but just stop the recording. So thank you everyone for coming, and thank you to Sofia and Mercedes for these really interesting talks, and see you everyone to the next QRSD.
Thank you very much. And there was a question in the chat, so I will just make sure everyone knows. Please follow us on Twitter or subscribe in Eventbrite if you don't want to miss the next seminar, and I believe me, you don't want to miss the next one. Okay, so thank you very much. I stop recording.